In some inclined plane problems, we can use our trig and use the ratio of sides instead of angle. So remember here, trigonometry, if this is our angle, A, B, C, sine of theta is opposite over hypotenuse. Cosine of theta, adjacent over hypotenuse. And then tangent of theta, opposite over adjacent. Okay. So sometimes we can use that. Like the height of something and the length, or the height and the length underneath. So, if we have a situation where we want to get like a coefficient of friction, then if we got something here on an inclined plane and it is at rest, that means friction is holding it there, okay? And remember, static is like a spring. You can think of it, it can match the force you apply up to a certain point. Then like a plastic spring could break. But you push something a little bit and friction matches it. You release it, releases. You push it slowly a little harder. Friction matches it, you release it. Because friction, the force of friction, can be up to that. And then once it gets there, it breaks and starts moving, you know, kind of breaks metaphorically, not literally. So, at different angles, friction will hold it. And then eventually there's some point where the thing just starts to move, where you're getting up to the capacity here. And so at that angle, once you get there, then the force of friction would match, it'd be like just equal to this. That's where the board would start to move. Because right you get there and the thing starts moving at constant velocity. So friction cannot hold it in anymore at a certain point. And that's the point. But when it starts to move, thinking about it this way, we know the force of friction will equal the component of gravity parallel along the board. Gravity's pulling it, you lift something up, gravity doesn't pull it much, then more and more and more, and eventually something starts to move down. Right when it starts to move at that angle, the parallel force of friction just matches that, and so it can move. So I don't have a demonstration right here handy, but you can get it with a 2x4 or a board. Get the board, 2x4, put something on it, start lifting it up slowly. Eventually something will move. Easy. So when this is the case, then this will equal that. But the normal force of the inclined plane is just equal to the perpendicular component of gravity. Because the board's just supporting the perpendicular component of the weight. And so then, with stuff we discussed before, parallel component, it'd be mg sine theta. It'd be this fraction of the weight. The perpendicular component is another fraction of the weight. So that's just another way of saying the force of friction is just the same as how much the force of gravity is pulling down the incline. Clearly, we can divide mg out. Then sine theta mu static cosine theta divide so sine theta over cosine theta is just tangent theta. So in this context, with our mathematical derivation, we can see that the numerical value of the coefficient of static friction is the tangent theta of the angle. Of course, I didn't tell us what friction is. Friction is something else, but we can use math, the power of mathematical thinking and quantification and measurement. We can use measurement to see another way to get what this number is, another way to express it. But clearly, that's not what friction is, because friction's on a flat surface as well. So in this context, we can get the coefficient of static friction by doing the tangent of theta, but notice the tangent is opposite over adjacent. So the coefficient of static friction is also height over length. The length from here to this, you know, it's like the base of the triangle. Height of the triangle, base of the triangle, think of it that way. This ratio will give you the coefficient of static friction. Then we could do something similar for kinetic. When something's moving down at a constant velocity, we can figure out what the ratio or the coefficient of kinetic friction is. So here is where something just starts to move, so we're talking about static. Okay? If something's moving at a constant velocity, then we do kinetic. But here, static. So let me see some problems. Yeah. There's the sliding. So look on this. I'm looking on this worksheet. I'll do some from here. Looks like these involve kinetic friction. Okay, so for static, we get that. I'll put it. Okay, and pretty much the same for kinetic, just a different angle. So when something's moving down at a constant velocity, then there's no acceleration. Constant velocity means acceleration is 0, means net force is 0. And so the forces acting on it would be friction and parallel force due to gravity. And so we got the same kind of thing again. And so go through the same derivation. And again, mu sub k is tangent theta, but it's going to be a different angle. This was just to start moving. This, for kinetic, you move the board until the thing goes down at a constant velocity. Okay. So in kinetic friction and static friction, the coefficients are usually always different. But there, do the derivation. And again, so We can just make it like that. Different situations. All right. Now, on this worksheet, so here, an inclined plane, 14 meters long. So here they're talking about this part. And would it go 4 meters high? Is used to load suitcases into an airplane. It takes a force of 35 newtons parallel to the plane to move a 100 Newton suitcase up the plane at constant speed. What is coefficient of friction? So here, let's see, we got more than just gravity, so we got something pulling it up as well. So in this case, on this thing, if we draw it, free body diagram, we have a force of 35 newtons to make it go upward. And then it weighs 100 newtons. And so force of 35 newtons parallel to the plane. So 100 newtons, the component downward, we'd have, we don't know this stuff yet, but along the plane, we have 100 sine theta. I'll put that part, let's say like F parallel, and then F friction. Remember, the parallel component will be mg sine theta, and that's going to be 100 times 9.8, and sine theta is opposite over hypotenuse, so 4/14. And so we get, and wait a second, oh, it weighs 100 newtons, so we don't need to multiply by 9.8. Weighs 100. So 100 times 4 divided by 14, 28.57. Turn the beeper off. Then the force of friction is the use of K times the normal force, which is just the perpendicular component of weight. And so this will be (100) cosine theta. The cosine is adjacent over hypotenuse, Pythagorean theorem. So we get, let's call it a squared plus 4 squared, 14 squared. So a squared plus 16 is 186. A squared is 180. Square root be like 13.7 or something. second square root 180 13.4. About 13.4. And so cosine is adjacent over hypotenuse. So this will be (100) times 13.4 over 14. So 1340 divided by 14. 100. 95.7. Okay. And so then we know that this equals z since it's constant velocity. Constant velocity, no acceleration, balanced forces, net force is 0. So net force is 0. So 35 minus F parallel minus F sub F is 0. So 35 minus 28.57 minus 95.7 b sub k is 0. Move this over, subtract 6.43, 95.7 b sub k, 6.43 divided by 95.7, about 0.067. Okay, not much. That's number 5 on this worksheet. Okay, let's do another one. So that was number 5. Now, let's see. Okay, let me go check something really quickly. All right, sorry, chicken in the oven. So, number 6, an inclined plane is 4 meter long and 1.5 meter high. So, an object that just slides down the plane at constant speed without being pushed weighs 75 pounds. Calculate the coefficient of friction. Okay, so this time, it's going down at constant speed, so we got kinetic friction. And so if we do Pythagorean theorem, we can get this, and 1.5 over this should be our answer. So 1.5 squared plus a squared is 4 squared, Pythagorean theorem. 2.25 plus a squared is 16. A squared is 13.75. Square root. Second square root, 13.75. 3.71. 3.71. So then as we saw before, coefficient of kinetic, h over L, because it's constant speed, so kinetic. But you know what they're calling the length, remember I'm calling this L, and that's h, so don't confuse it with that. So 0.404. Okay. Number 7. We have an inclined plane as an angle of elevation of 20 degrees. Carton weighing 150 is to be moved up the plane. Coefficient of friction is 0.3. What force is needed to move the carton up the plane at uniform speed? So angle, carton weighs 150. 150 newtons, 20 degrees, 0.3. What force is needed? So on our object, we need some force, applied force, making it go up. And if it's going that way, friction's always in the opposite direction. We got the parallel component of weight pulling it down. And so we need this to equal these for constant velocity. Constant velocity means no acceleration. So if A is 0, this equals 0. The net force is 0. It's balanced. So then F is to E be F sub F plus F parallel. Then it's got to match those two. But the force of friction is coefficient of kinetic times the perpendicular, because the normal is a perpendicular component of gravity plus a parallel. And then that's mu sub k mg cosine theta plus mg sine theta and factor out the mg. So, or just put the numbers in and work it out. Either way, we get 0.3 sine of cosine 20 plus sine of 20 times 150. It gives us the weight already. So our perpendicular, our parallel, our calculator. So parenthesis 0.3 cosine 20, close parenthesis, plus sine 20, close parenthesis, 150, enter. Got 93.6. So about 93.6 newtons. Cool. So there are a few inclined plane problems on this worksheet. I'll put a link to it in the description field.